Welcome to this explainer. Today, we're going to completely transform how you view electric fields. Now, if you've been studying electrostatic forces, you already know that dealing with complex vector math can be, well, pretty daunting. But what if we could shift our perspective? What if we move away from that complex, multi-directional math and instead look at it as a simple, intuitive landscape? Today, we're diving deep into the core concepts of electrostatic potential and capacitance, literally mapping out an invisible topography that governs exactly how charges interact.
So here's the fundamental problem we run into. Calculating the net electric field from multiple charges requires vector addition, which basically means you're constantly worrying about angles, directions, and really complex geometry. It's a lot. How do you measure and predict the behavior of an invisible force without using all those complex vectors? Well, to solve this mathematical headache, physicists use a brilliantly clever shortcut, a scalar landscape. By assigning just a single numerical value to every point in space, we can map out the energy potential without ever drawing a single vector arrow.
Here is our syllabus for today's ascent. First, the electrostatic landscape. Second, mapping equipotential surfaces. Third, calculating electric potential. Fourth, storing potential energy. Fifth, dipoles in external fields. And finally, an introduction to capacitance.
All right, let's jump right into part one, the electrostatic landscape.
I want you to picture yourself pushing a massive, stubborn boulder up a really steep hill. The higher you push it, the more work you have to do against gravity, right? And consequently, the more potential energy that boulder gains. Moving an electric charge through an electric field operates on that exact same physical principle. This brings us to our formal definition. Electric potential, which we represent with a capital V, is simply the amount of physical work it takes to bring a unit positive test charge from infinitely far away, where the potential is considered to be exactly zero, to a specific coordinate in space, working against the electrostatic field. Put simply, it's a measure of the work done per unit charge.
Now, potential is what we call a scalar quantity, meaning it doesn't have a direction, it's literally just a number. And crucially, only the differences between 2 points actually have physical meaning. So when we talk about voltage or potential difference, we're really just measuring the mathematical difference in the scalar value between point A and point B.
Notice the stark contrast here between the electric field and the electric potential. While the electric field is a vector that drops off incredibly steeply, it's proportional to 1 over r squared, the potential is a scalar that decays much more gradually, just as 1 over r. Because potential is a scalar, if you have a system of multiple charges, you can literally just add their potential values together algebraically. No vector resolution required at all. It is a massive time saver for sure.
Moving right along to section 2, mapping equipotential surfaces.
Just like a hiker relies on contour lines on a map to find flat ground on a steep mountain, physicists use what we call equipotential surfaces to map out and navigate these electric fields. And these electrical contour lines follow some strict, unbreakable rules. First, the potential is constant everywhere on the surface. Because of that, absolutely zero work is required to travel along them. You aren't moving up or down the electrical hill. Second, the electric field lines always cut through these surfaces at a strict 90-degree perpendicular angle. Third, they never intersect because, well, a single point in space can't have 2 different potential values at the same time. And finally, just like topographical maps, when these lines are packed closely together, it tells us we're looking at a steeper hill, meaning a much stronger electric field.
This leads us directly to the beautiful mathematical relationship between the electric field E and the potential V. E equals negative dV over dr. But what does that actually mean in plain English? It means that the electric field represents the spatial rate of fall of the potential. Basically, the field always points straight downhill toward the lower potential. And its magnitude, its strength, perfectly matches the steepness of that potential landscape.
Let's tackle section 3, calculating electric potential.
Let's strip it down to the simplest building block we have, the point charge. For a single point charge, the potential V equals 1 over 4 pi epsilon 0 times Q over R. It's directly proportional to the magnitude of the source charge Q and inversely proportional to the distance R. If you were to map this out in 3D, it creates these concentric, spherical equipotential surfaces wrapping around the charge, spreading further and further apart as the field gets weaker.
Check out how the physical geometry of the source actually changes the landscape. Compare how this potential drops off depending on the configuration. A point charge decays gently as 1 over r. But an electric dipole, which is two opposite charges separated by a tiny distance, creates a potential that depends on both distance and angle, decaying way faster as 1 over r squared. And what about a complex system of many scattered charges? Easy. We simply calculate the kq over r for each individual charge and just add those scalar numbers together algebraically.
Which brings us to section 4, storing potential energy.
You know, when we do all that hard physical work to move external charges into this existing landscape, that effort doesn't just magically disappear. Thanks to the conservation of energy, it gets stored directly as potential energy. The formula for this is remarkably elegant. U equals Q times V. A charge, Q, placed in an external electric field holds a very specific amount of potential energy, U, which is exactly equal to its own charge multiplied by the ambient electric potential V at that exact coordinate in space. The landscape itself provides the potential. The charge you drop into it determines the actual stored energy.
So the really crucial takeaway here is how these charges naturally want to behave in this environment to minimize their energy. A positive charge will naturally be pushed in the direction of the electric field. It rolls downhill from a region of high potential to low potential, decreasing its potential energy. But negative charges, like electrons, they're kind of the rebels of the microscopic world. They naturally move against the field lines, effectively falling uphill, from low potential to high potential.
Now for section 5, dipoles and external fields.
So we know how a single charge behaves, but what happens if we take an electric dipole, two tied equal but opposite charges, and just drop it into this invisible, uniform topography? Because the dipole consists of both a positive and a negative charge connected together, an external uniform electric field will actually pull them in opposite directions. The field grabs both ends of the dipole, creating a torque, a twisting force. This torque, which we calculate as P times E times the sine of the angle theta, desperately tries to twist the dipole moment until it rests in perfect alignment with the external field lines.
Now, manually rotating the dipole against this twisting force requires external work. And, you guessed it, that work is stored as potential energy. The potential energy of the dipole is U equals negative PE cos theta. This means the energy is at its absolute minimum, its most stable, happy equilibrium when it's perfectly aligned with the field at 0 degrees. Conversely, that potential energy absolutely peaks when it's perfectly anti-aligned, fighting the field at 180 degrees.
Finally, we arrive at section 6, Introduction to Capacitance.
Since we've established that this landscape can store energy purely in the physical arrangement of charges and potentials, how can we engineer a system to maximize this exact capability? Well, this brings us directly to the concept of capacitance. Capacitance is, very simply, the physical ability of a system to store electric charge and, by extension, electrical energy. We measure this incredible capability in a unit called the farad, denoted by a capital F.
Formally, the definition of capacitance is the ratio of the charge stored on a conductor to the potential difference applied across it. By carefully engineering a massive potential difference between two conducting plates separated by an insulator, we are effectively building a steep artificial cliff in our electrical landscape, and by doing that, we can bottle up incredible amounts of energy. A parallel plate capacitor does exactly this.
We've seen that by utilizing the scalar nature of electric potential, we can easily map the invisible forces acting on charges, calculate the stored energy, and even begin to engineer devices like capacitors to hoard that energy for our own practical use. But this leaves us with a genuinely fascinating engineering challenge to think about. If potential is just a landscape, and a capacitor is a steep cliff we've intentionally built into it, how steeply can you stack this topography? How much voltage can you apply before the physical dielectric material simply breaks down and sparks? Keep that provocative thought in mind as you continue exploring the amazing world of electrostatics.